All right, let's turn our attention now to talking about the stability of a system. We've spent a lot of time working through lots of different examples and really kind of the mathematical mechanics of how you compute the response or the output of any LTI system. So we've gotten a lot of practice with that. What we're going to do now is we're going to learn how to classify systems based on these responses. So now that we know how to compute the responses, let's analyze the types of responses we see sometimes and use that to classify systems based on what we call their stability. How do their outputs behave? Are they well behaved, or do things blow up, or do they oscillate? Depending on the nature of the output, that's how we will classify our system. So first of all, just some definitions. What do we mean by a state? So if a system tends to remain in a particular state for an indefinite amount of time, that's what we call an equilibrium state. So if you tend to be in this one particular condition for a great amount of time or some undetermined amount of time, we call it an equilibrium state. And these equilibrium states we classify in three different ways. One of them is what we call an equilibrium state. And this is a state that your system comes back to if it is disturbed. So imagine your system sitting there maybe having zero output, right? It's doing nothing, just outputting zero. You hit it with an impulse, your system responds and does something, but then a few seconds later it's decayed and it's back to zero. So that would be an example of a stable equilibrium state. The system was perturbed and then it came back to the original state it was in. So we call it stable equilibrium. An unstable equilibrium is not like that. These unstable equilibrium states kind of diverge from where they're at. So maybe you have a system sitting there just oscillating, right? Maybe its output's just oscillating back and forth like in a sinusoidal fashion. Then you disturb the system. Maybe you hit it with an impulse or you put in a step or something like that. And then you take the step off or you let the impulse decay. But instead of coming back to the sinusoid, maybe the sinusoid amplitude continues to grow and it diverges away from the constant amplitude sinusoid that you were at. So originally it was doing its thing, it was sitting there oscillating back and forth, but after being perturbed with some input for a second, it diverged away from that. And the key kind of there in that thought experiment was, as it was oscillating originally with a constant amplitude, after being disturbed, the amplitude kept growing without bounds. So it's just blowing up and going unstable. The last type of equilibrium is what we call a neutral equilibrium. And this is an equilibrium state that doesn't go back to its original state, but it also doesn't move further away from the state. So go back to our system that has a sinusoidal output with constant amplitude oscillating back and forth, just sitting there, oscillating back and forth. Here, though, when we disturb it, instead of just blowing up and going off to infinity in terms of amplitude, maybe the amplitude changes to a new amplitude that's double the height, and then it just sits there for forever. So picture an amplitude of height 1 sinusoid oscillating. You disturb the system briefly, and now the amplitude increases to 2, but it just keeps oscillating at 2. So in that case, it's not continuing to go further and further away, and it also hasn't gone back to where it was, a unit amplitude oscillation. So that's what we call a neutral equilibrium. All right, now that we kind of have this concept of state and returning to states or leaving states, let's talk about the definitions of stability that we'll use for this class. When we talk about LTI systems, we say that an LTI system is stable if it returns to its zero state when disturbed. So that was the example I gave on the previous slide. If you have a system doing nothing, you hit it with some type of input for some period of time. Once you've removed that input, the system eventually decays and goes back to the zero state. That's what we mean by a stable system. If this happens, that tells us something about the characteristic modes. The characteristic modes have to go to zero as time gets big. An unstable system, that does not happen. An unstable system does not come back to its zero state. It moves further and further away from the zero state when it is disturbed. And this will happen anytime that you have characteristic modes that grow as time gets big. We say that an LTI system is marginally stable anytime the zero input response is bounded but doesn't come back to the zero state. So here, I was at 0, I got perturbed, I came back to 0, stable. Here, I was at 0, I got perturbed, and I blew up. That's what we call unstable. Here I'm at 0, I get perturbed, and I don't go back to 0, I don't go to infinity. I maybe just go to a constant number and hold there, or maybe I go to some oscillation whose amplitude remains constant. So this is the one that's in between again. So we have these three concepts of stability: stable, unstable, marginally stable. The marginally stable here is going to have characteristic modes that don't get bigger or smaller with time. They just kind of oscillate, so kind of oscillatory behavior. But all of these are tied very much to the characteristic equation roots, because the characteristic equation roots are what determine the characteristic modes, and the characteristic modes are what determine whether a perturbed system returns to the zero state, blows up, or oscillates over time. So to be able to classify a system, whether it's stable, unstable, or marginally stable, really what it boils down to is finding the characteristic equation and figuring out where the roots are. So let's think about that, and let's tie what we just talked about in terms of states and equilibrium to the root locations themselves. So how does a stable system have roots in the complex plane? Well, it turns out that a stable system is always going to have its roots in the left-hand plane. It has to have them in the left-hand plane because we need these characteristic modes associated with those roots to die down over time. If you have a root in the left-hand plane, say on the real axis at -3, that corresponds to a mode of e to the -3t, which decays with time. So stable systems have all their roots on the left-hand side. An unstable system is opposite. It has at least a root on the right-hand plane. So let's say I had a root at 2. Well, that corresponds to a characteristic mode of e to the 2t, which blows up with time. So if I have any roots anywhere on the right-hand plane, I am an unstable system. Or if there are repeated roots on the imaginary axis. Being on the imaginary axis typically corresponds to some type of oscillatory behavior, but a repeated root we know throws an additional t term, and that would correspond to some type of oscillation that's also growing in amplitude, as a function of time. Marginally stable systems have their roots on the imaginary axis, but they're not repeated. So no roots in the right-hand plane. If there were, we'd be unstable. We can have some roots on the imaginary axis, but these roots are not repeated. And then finally, we've talked about this concept of bibostable before. Bibostable means if I have a bounded input, I always have a bounded output. If I'm stable, meaning all my roots are in the left-hand plane, that means I am also bibostable. So given that I'm stable, I'm also bibostable. Those are kind of one and the same for us. So here's just a picture of what we were talking about. It kind of quantifies it. This is the complex plane, real axis, imaginary axis. This is what we call the right half plane. If I have any roots over here anywhere, I'm unstable. This is what we call the left-hand plane. If I have any roots over here, I am stable. If I have any single-order roots on the imaginary axis, that means that their real component is 0. Then I'm a marginally stable system. If I have any repeated roots on the imaginary axis, then I am an unstable system. So let's walk through just a few examples here, just kind of cartoony, but these definitely capture what we've been talking about. Let's look at the location of a root in the complex plane. So here is a root at -1, and see what its zero input response looks like. So since this is at -1, I have an exponential e to the -t decaying with time. So this is how the root in the complex plane determines my zero input response and how my system responds asymptotically. So here I've changed my root location from -1 to 0. A root at 0 corresponds to a zero input response that's a constant 1. This is basically an oscillation with DC frequency. So it's just a constant 1. So you can tell we're marginally stable here. If my system gets perturbed, I just kind of asymptotically hold this 0 value. I don't blow up, but I also don't decay to 0. So this is what we call marginally stable. What if I have a second order pole? So here I have a second order pole denoted by that 2. Well, now I'm definitely unstable. I have repeated roots on the imaginary axis. This corresponds to my constant value times t. So this blows up as a function of time. It's unstable. Here's a pair of complex conjugate poles. Both poles are in the left-hand plane, so I am a stable system. this corresponds to a zero input response that's oscillatory, but the amplitude is decaying with time. As time goes on, this decays and it eventually goes back to zero. If I move poles further out on the imaginary axis, moving in this direction increases the oscillation rate. So how quickly I oscillate is determined by where I'm at along the imaginary axis. The further up I am, the faster I oscillate. So this looks very similar to the last chart in terms of how it's decaying. It's just how it oscillates is much faster because I'm further along the imaginary axis. What if I move those two things to the imaginary axis? Well, now I'm back in the marginally stable case. I'm going to have oscillatory behavior because I'm off at 5 and -5, so that's going to determine the frequency of oscillation. But since I'm right on the imaginary axis, I'm not going to decay or blow up. I just hold this constant value for all time. If I move those just slightly to the right, so now I have poles in the right-hand plane, they're complex conjugates, so I know I'm going to have oscillatory behavior with frequency 5, but since these are now in the right-hand plane, my amplitude is growing with time, and this is now an unstable system. So that was just kind of a sequence of kind of cartoon results, keeping it very simple, just one or two poles, and how these pole locations or characteristic root locations map to the zero input response, because we know that these root locations determine the modes of the system. The modes of the system determine the natural response, yn of t, which is part of the impulse response. So a system that's sitting there at rest that gets hit with any type of input is going to respond based on where these roots are located.